All right, today we're going to pull back the curtain on something pretty wild, the speed hacks that make these huge language models feel instant. And let me tell you, it's not magic, it's just some really, really clever engineering. I mean, have you ever stopped to think about how insane this is? You ask a question, and these models with billions of parameters, way more connections than our own brains, just fire back an answer in seconds. This isn't just looking something up, right? This is some heavy-duty computation. So how on earth do they do it? Well, the secret is a whole stack of really clever optimizations, a whole cascade of them, really. Each one is designed to shave off tiny fractions of a second and huge chunks of memory. So let's start peeling back those layers one by one, and we're going to start right at the core engine of the model. Okay, so deep down inside every single modern LLM, you've got this thing called self-attention. Honestly, the best way to think about it is like the model's ability to focus. As it's generating a sentence word by word, it's constantly looking back at everything it's already written down. It's trying to figure out, okay, which of these past words are the most important for deciding what I say next? So how does this whole focusing thing actually work under the hood? Well, for every new word it's about to generate, the model creates what's called a query. You can think of this like it's asking a question. Hey, based on everything so far, what stuff is actually relevant right now? It then takes that query and compares it to a key for every single previous word. This gives it a score, like an importance score. Then it uses those scores to mix together the values of all the previous words, and boom, the result is an output that's just loaded with all the right context. But here's the thing, a single one of these attention calculations can only really focus on one kind of relationship at a time. To get around this and make the models way more powerful, engineers came up with something called multi-head attention, or MHA for short. Just imagine having like dozens of these little attention mechanisms all running at the same time in parallel, and each one is looking for a totally different kind of pattern in the text. And look, there's a good reason MHA became the default. It's what lets the model get all the nuance, the grammar, the meaning, all at the same time. It's super powerful, it's stable, and it's great for running on GPUs. But, and this is a big but, it has one huge, glaring weakness that created our very first major performance problem: memory. So with standard multi-head attention, this MHA we've been talking about, every single one of those little heads needs its own private copy of all those keys and values. The analogy here is perfect. Imagine you have 100 researchers and each one needs their own private, personal library. Yeah, it's thorough, but it's also unbelievably inefficient, right? So the first big hack was something called multi-query attention, or MQA. And it basically asked a really simple question. What if, instead of 100 private libraries, all the researchers just shared one massive central library? Now, MQA was definitely fast, but it turned out that sometimes it sacrificed a bit too much quality. The researchers were bumping into each other, so to speak. So the community came up with this brilliant compromise: grouped query attention, or GQA. It's like the Goldilocks solution. Instead of one giant shared library, what if we create a few smaller shared libraries? You split the researchers, the query heads, into groups, and each group gets its own shared library. It's the best of both worlds, really, and it's exactly what's powering the big models today, like Llama 3. And this table really lays out the whole trade-off perfectly. You've got MHA over on one side, best performance, no question. But it's slow, and man, it just eats up memory. Then on the complete other end of the spectrum, you have MQA. It's lightning fast, super lean, but you might see a little dip in quality. And right there in the middle, that's GQA. It's the sweet spot. You're getting performance that's almost as good as MHA, with speeds that are getting really, really close to MQA. And hey, this isn't just theory. Check out these real-world numbers from a Llama 3 model. Just by switching from the standard MHA to GQA, you're knocking off about 16% of the response time. That's huge. Yeah, MQA is a little bit faster still, but for a lot of people, GQA's ability to keep that quality high makes that tiny speed difference a totally worthwhile trade. All right, so we've got a much faster attention architecture now. Problem solved, right? Well, not quite. There's another, maybe even bigger inefficiency lurking. See, when an LLM writes text, it does it one word at a time. And the crazy part is, for every single new word it adds, it was recalculating all of those attention scores for the entire history of the conversation, right from the very beginning, every single time. Which just makes you ask, why? Why would you recalculate something you already know? I mean, the keys and values for all of the previous words, they haven't changed at all. Come on, there has to be a smarter way to do this. And of course there is. It's called the KV cache. And this thing is basically the model's ultimate cheat code. It's like a short-term memory. It just stores all those key and value vectors that it's already calculated, so when it's time to generate the next word, it doesn't have to redo all that work. It just calculates the K and V for that one new word and then grabs all the old ones from this super fast cache. Simple, but brilliant. So the KV cache is an absolute game changer for speed. It makes generating long stretches of text way, way faster. But you know how this goes. By solving one problem, we've just created a brand new one. Another bottleneck. And this time, it's memory again. Because that cache, it has to be stored somewhere. And with every single word you add to the conversation, it just gets bigger and bigger and bigger. So just how big are we talking? Well, get this. For a pretty standard 10,000 word context window, which isn't even that big anymore, the KV cache by itself can take up 5 gigabytes of that super expensive GPU memory. That's insane. That's 5 gigs that can't be used for the actual model weights, which means it puts a hard limit on how big and complex of a model you can even run. Okay, so how do we fix this memory problem? Well, that brings us to our final hack, a technique called quantization. Now, it sounds complicated, but it's really just a fancy word for making numbers less precise. The JPEG analogy is absolutely perfect here. You know how you can have a giant, high-resolution photo file, or you can compress it down to a much smaller JPEG. You lose a little bit of detail, sure, but most of the time you can't even tell the difference. Well, we can do the exact same thing to the numbers we're storing in that big old KV cache. So by quantizing that 5 gigabyte cache, we can shrink it down a lot. And that means we can handle way longer conversations using the exact same hardware. But just like with that JPEG, you are losing a little bit of information. And this leads us to our final and honestly, probably the most interesting trade-off of them all. This quote I found on Reddit just nails the whole dilemma. A user, u/gl-ai, said, "In my experience, if you're coding or doing something that requires precision, quantizing the cache is definitely not worth it. If you're just chatting, it's 1,000% worth it." And that's it, right there. If you're doing something creative, having a casual conversation, that tiny loss in precision doesn't matter at all, and having that extra memory is amazing. But if you're doing something like coding, where every single detail has to be perfect, that tiny loss can become a huge headache. And check this out. Here's another story that makes the point even better. Another user, u/mutant eggroll, posted that they were having great success using a quantized cache for coding. But then they added an edit completely retracting the above, reverting to unquantized KV cache has effectively fixed it. So they were running into these weird, subtle bugs they couldn't figure out. As soon as they switched back to the full precision cache, poof, the problems were gone. It just shows you how much the right setting matters for the task at hand. So really, it all boils down to this, what I like to call the performance triangle. You've got 3 competing priorities. On one corner, you have accuracy or quality. That's what quantization messes with. On another corner, you have speed or latency. That's all about your attention architecture. And on the third, you have memory, which controls your cost and how long of a conversation you can even have. And here's the kicker. You can't have it all. You can't maximize all 3 at once. If you push on one corner of this triangle, you're always going to pull back on another. And what this all means is that the single most important thing to understand is this. There is no single best setting. There's no one-size-fits-all solution. The best setup isn't some fixed thing out there to find. It's a choice that you have to make based on what you're actually trying to do. Are you trying to build a super precise coding assistant or a fun, creative chatbot? The answer to that question completely changes which of these trade-offs you're willing to make. So the next time you're firing up a chatbot or picking a model for a project, you'll know what's going on under the hood. You'll understand this constant battle between accuracy, speed, and memory. You're not just a user anymore. Now you're an informed operator, equipped to choose the right tool with the right settings for whatever job you have in mind. So the question is, how will you choose your next model configuration?